welcome you all in this lecture. So today's lecture is particle in one-dimensional box. So particle in one-dimensional box, this is, as you know, is an application of Schrödinger wave equation. So here we will discuss how does a particles is behaves in one-dimensional box and what type of relationship in case of the energy, how we can find out the energy of a particle in one-dimensional box. So here we will discuss, before going to that, here we will see how a particle in a box can be and its derivation for a particles in one-dimensional box, and how can we find out the, or we can check the quantization of energy, existence of zero point energy and non-quantization of energy for the particles. So from here, so before moving to the topics, let us see an experiment in which a vibration has been made in a silicon oil which is kept in a vibration state here, in vibration state, and suppose a droplet has been put on this, then this droplet will also make a number of vibrations in that particular liquid. So here, because this will create a different wave like nature or different waves on the surface. So Louis de Broglie, as you know, he has given the dual nature, or that is the dual nature of the light or particle as well as wave kind of nature. So because here, like suppose if it is a particle like our nature, or suppose it is having a electron which is moving in a particular path, so then it is easy to locate. But what happens when it moves in a particular area in case of wave? So then how can we locate it and what would be the probability of this? So this is what is being explained on the basis of Schrödinger wave equation, because that is why this is comes with a particle in one dimensional box. So like in a box, suppose the wave is going in particular direction in one dimension or two dimension, then how can we can explain it? So in 1935, Erwin Schrödinger, in an experiment or hypothetical experiment, he put in a case a cat and poison with Geiger counter having some inside radioactive material. So there is, now if there are, after some time, suppose there is some particles or some radioactive material comes, so there is a probability of finding the probability of whether the cat will be live or not is depends on the probability factor. Means either it can hit, or this, and this poison can release out and cat can die, or it can also happens that if the radioactive material does not release, so the cat will be live. So this is an hypothetical experiment. He seen that the similar way. So here there is superposition. He said that there is a probability of finding, like in case of electron, probability of finding the electrons in a particular area. So similarly, if it is being live, so the probability which is represented by wave function psi a plus ib. If the cat is died, so that can be psi star a minus ib. So this can be represented by a mathematical, the equation which he has given, psi into psi star probability of finding the electron, that is psi star, and can be also represented as in a modulus form a square minus I square v. So by this way, means in a particular area where the electrons can be find in case of is a very complicated process, because this is not so easy to find out. So in case of like in a wave kind of nature, then how particles or either electrons or particle in one dimensional box, how can we find out, is being given by the Schrodinger, and the one dimensional box is the application of Schrodinger wave equation. So here a particle in a box provide us the application of Schrodinger wave equation to the translational motion for particle in an electron atom or electron or small particles. It also explains to why the energies associated are quantized. So the motion of the particle in one dimensional box is like the flow of an electron in a wire, but still is called particle in box. And a general case can be considered in which we may assume that a single particle like a gas molecule of mass having m is restricted to move in a region of the space x equal to 0 to x equal to a. So this is the space from where these particles can move, and it is a potential, and its potential energy within the box is considered and taken as equal to 0 for the sake of convenience. So here you can see, like in a particle in a one dimensional box, so inside the box the potential energy is constant to all, so this is taken as 0. At outside the box this will be taken as infinite. So like x equal to 0, so x equal to a, within this space the electron is restricted. So particle is one dimensional box, as we already said, potential energy inside the box will be 0, and on the wall of the outside of the, and you can see outside of the box the potential energy is infinite. So here, in order to the particle may remain within the box, it is essential to assume that the potential energy on inside the box will be 0 and outside the box will be infinite. So here you can see, as per the Schrodinger wave equation, which we have already discussed. So as per the Schrodinger wave equation, so because there we had seen it for 3 coordinate, but for one dimensional box on one axis, so the Schrodinger wave equation is del square or d square psi upon dx square plus 8 pi square m upon h square into e minus v into psi equal to 0. Here the psi is a wave function as taken as a function of x coordinate only, and you also know at the outside of the box v equal to infinite. Therefore outside the box the equation will be become del square psi upon dx square plus 8 pi square m upon h square into e minus v into psi equal to 0. So just assume this is an equation 1 and another one is equation 2. So after neglecting the e in comparison to infinite, so the equation will become reduced to d square psi upon dx square minus infinite psi, since one you will multiply this value 8 pi square m upon h square with infinity, so the value will also come the infinity. So in a simplified way we can write this equation d square psi upon dx square equal to infinite psi, or psi you can make an interchange, or you can just rearrange the equation. So psi will be 1 upon infinite into d square psi upon dx square will be equal to 0. So this equation proves that the outside the box psi equal to 0, which implies that the particle can have the restricted inside the box. For the particle within the box, the v equal to 0. So therefore Schrodinger wave equation takes the forms which we can also write in this way: d square psi upon dx square plus 8 pi square m upon h square into E psi. So for the given state of the system, the energy E is constant, which is one of the postulate of the quantum mechanics. So therefore we can put 8 pi square m upon h square into E in a simplest way, can be represented by k square, and this is in a constant. So this terms can be replaced with the k square, and this k is in a constant and it is independent of x. So x means that particular position from where that is the you are finding the probability. So here the equation 4 then will be becomes, it will take another shape. So let's see what is that. So d square psi upon dx square plus k square psi equal to 0. So a general solution for this differential equation is given by, as you know, this equation is generally given by this form: psi equal to a sin kx plus b cos kx. So here you also know a and b are constant. So depending upon the value of a and b, and k and psi can have many values, but all the values are not acceptable. Only those values of uh, y are acceptable if they satisfy the boundary condition, which is psi equal to 0 at x equal to 0 and x equal to a. So there are certain conditions. On the basis of those conditions, only these equation will fit, will be only acceptable condition will be like this way. So now coming to the another here, if you can further simplify, so putting psi equal to 0 when x will be 0. So equation 7 will be becomes, will take the another form: 0 equal to b sin 0 plus b cos 0. So you know sin 0 equal to 0 and cos 0 equal to 1. So the final form, it will take the equation once the x will be 0. So equation 7 becomes will be psi equal to a sin kx. Now putting the value of 0 when x equal to a becomes equation a, this equation 8 becomes, will take another shape: 0 equal to a sin ka or sin k equal to 0. And this equation holds good only when the values of k are integer multiple of pi. Also you can say ka equal to pi or ka equal to n pi, and you know the n is the integer value like these values. So however, like 0 1 2 3, but the value n could be excluded because it makes the overall this value k value will be 0. So for psi equal to 0, for any value of between 0 and a within the box, this is not true because the particle is always assumed to be present within the box. So k can be seen from this equation n pi upon a. So this can take another form of the equation. So this value of the k can be put over on the equation number 8. So you will get this equation will take the another shape like psi equal to a sin n pi upon a into x. So this gives the expression for the eigenfunction y. The expression for eigenvalue of the energy may be obtained by the following equation from, it took from the equation 5. So that equation 5 will took the shape of this. So E will be k square h square upon 8 pi square m. So from here you can calculate the energy. So this is the energy equation. Also you can say this can be helpful to calculate the energy. So substituting the value of k from equation 11, you will get this form: n pi upon a square into h square upon 8 pi square m. So after solving this, after making it in a simpler form, it will take the shape equal to n square h square upon 8m a square. So example 12, equation 12 and 14 are the solution of the Schrodinger wave equation for one dimensional box. So this is overall, you see the one-dimensional box. You will find the solution in an energy equation which will take the shape n square h square upon 8ma square. So this is the are the solution for the Schrodinger wave equation for one-dimensional box. So now you see the expression for energy in a particle in one-dimensional box, you can represent by this. So here m is the mass of a particle and a is the length of the box. So it is the box length, from 0 to like x, or x is having the value of a. So this is the distance from where you can assume the particle in one direction or in x coordinate. So now there is a certain quantization of energy can be find out from this equation. So how we can see here, we can see since n can have only integral value equal to 1 2 3 etc., therefore equation it follows that the energy associated with the motion of the particle in box uh, can only discrete values, or you can say having the energy which is having the quantized energy. So the integer n is called the quantum number or of the particle. So this is further putting n equal to 1 2 3, you will see the discrete energy level will obtain for the particle of mass m and confined in a box of the length ar, can shown here like this figure. So discrete energy levels of a particle of mass m confined in a box of length a can be seen from this here. If the value of n equal to 1, so then as per the equation, energy equation, that is n square h square upon 8 pi square 8m a square. So putting the value of n will be 1, so the equation will take the shape of h square upon 8m a square. And when you will take the value of n equal to 2, so the equation will be 4, it means 2 square h square upon 8m a square. After solving this, you will see this is 4h square upon 8m a square. Similarly 3 you have to put in place of n square, so 3 into 3 will be 9, so 9h square upon 8m a square. And similarly once you will put the value of n equal to 4, so this will be 16h square upon 8m a square. So it means here you can see by putting the value of n, or you can say the quantum number, then the discrete energy levels can be obtained with the help of for one-dimensional box with the help of Schrodinger wave equation. And similarly these equations are helpful to see the quantization of energy in case of two-dimensional box and three-dimensional box, which we will discuss later. So here with the help of Schrodinger wave equation, you can see how it can be helpful to check the discrete energy levels of a particle having mass m and which is confined in a box of a certain length, which is being assumed here like from x equal to 0 to x equal to a, we can assume. So it is important to note that as the quantum number increases, the separation between them they will also increase, because due to the value of the equation is getting to be changed. It may also be noted that energy level also depends upon the box length, and as increase the space available to the particle increases, because the particle will have a more space to there is a probability of the finding the electrons will be more in a different places. So energy quanta becomes smaller and energy levels more closer or together. If the box length becomes very large, quantization disappears and there is a smooth transition from quantum behavior to the classical behavior or continuous change. So once the space is being, like macroscopic species compared to the small species, microscopic species, as we discussed in initial lecture, that the quantum principles is more helpful to explain the nature of a microscopic species. So once you increase this the space, or increase the then obviously the quantization will disappears, and there is smooth transition from their quantum behavior to classical behavior will be change of, or continuous change will be seen in the explanation. So the minimum value of n could be only 1, because for the ground state energy the n will be the 1. Since n equal to 0 is ruled out, as we discussed during to explanation of the Schrodinger wave equation, so substituting the value, then we will see n square. If you put the number n equal to 1, then obviously this equation will take the shape equal to h square upon 8ma square. So this is also called 0 point energy. So here the meaning of 0 point energy does not means you have to put the value of 0 equal to in n, in the place of n you should not put the value 0. It means from the ground state, the as per the as we discussed in earlier in a Bohr models. So uh, because that h, if you will put the n value 0, then obviously this whole value will comes 0. So that is not taken. So in a ground state energy or 0 point energy, even once if it is asked to calculate the 0 point energy, then you have to put the value of n equal to 1. So the overall solution will come equal to h square upon 8ma square, and then you will be able to calculate the 0 point energy or ground state energy for a particle in one dimensional box. And if the, like in non-quantization of energy, if you want to, that is you want to calculate for the particles, since if the walls of the box are removed, suppose just assume if the walls of the box are removed, so that the particle is free to move in a field whose potential energy value do not follow any restriction. Because once, if suppose as we discussed earlier here, if the particles restriction is removed, then obviously there is no restriction for this value, so it will not follow as a restricted area. Then the boundary conditions are no longer applicable, because once you had set the boundary conditions like x equal to 0 to x equal to a, and inside the box the potential energy equal to 0. So since you are removing that condition, then obviously the boundary condition once are you are not applying, so it will be no longer applicable. And so the constant a and b and k can have any value. So the energy of the particle is then given by the equation equal to k square h square upon 8 pi square m. So as the constant k have any value, the energy of the free particle is not can be can be, if it is like a constant, then in this way you can find out the energy uh, for the particle by this equation k square h square upon 8 pi square m. So here the all terms are as usual meanings, mass, Planck's constant, like in case of, if suppose you are talking like h square. So the m, the mass of the the mass of the particles. So by in, if suppose you are removing this condition, non-quantization, or if suppose the non-quantization of energy for the particle you want to calculate, or you want to calculate the energy, so you have to follow up this equation. So now overall, if you see from the past, the discussion, We discuss today's lecture in a particle in one dimension box, which is basically the application of Schrodinger wave equation. In case of like in a small particles or microscopic species, like in case of here electrons and atoms, so that can be explained with the help of Schrodinger wave equation, which is called Schrodinger wave equation. So derivation, we had seen how to derive the equation for energy equation for particle in one dimensional box with respect to or with the help of Schrodinger wave equation. And quantization of energy, quantization of energy, we also seen uh, how the energy is like in a quantized form, going from the quantum level, like n equal to 1 or n equal to 2, n equal to 3, n equal to 4. So how can we find out the energy in different discrete levels, and by putting the value of the n, by that way you can also calculate the energy. So that is being very important, and many more example is also available. So quantization of energy and existence of 0 point energy, as I said, here the value of n will be put as a 1, or like in case of suppose if it is asked the ground state energy, so even though the value of n will comes n will be 1, not as a 0, otherwise the overall solution will not give the correct answer. So ground state or state energy and first excited energy, first state of energy, or second excited energy, excited state, and third, or like that. So n value will be changed from 1 2 3 4 like that. So by that way you can also find out the 0 point energy, and as you know, by this way you can get a different discrete energy levels. So with the help of particle in one dimensional box, you can also can check it out. And if you see in terms of non-quantization of energy, so there is certain conditions for finding out this energy for a particle. So what are those conditions? Because if suppose because already we as discussed for a particle in one dimensional box, and we restricted the particle in one particular area. So we are just finding the because that there is the particle, if suppose you want to find out the energy for such kind of particles. But if suppose there is some which is the restriction in case of one dimensional box. So if suppose you remove those restriction, and if the particle is free to move, then that equation will change up. The energy will also you will calculate in a different way. And if the distance you increase, if it is a very high distance is there, and it is very the particle is very longer space is available, or there is no condition is of restriction, then it will not behave like a quantum mechanically, or it will the relevance of calculating the energy has no meanings, and it will be like in a classical or continuous kind of behavior it will show. So that is very important. So here overall, if you see, we discuss about the particle in one dimensional box, their derivations, how to derive it, and what is the relevance of quantization of energy, 0 point energy, and quantization of energy and non-quantization of energy for the particle. So here are some of the questions which is generally being can be very important for explaining, like explain in brief about the application of particle in one dimensional box, and drive an equation for the particle in 1D box, and these are the basic questions which can be made from these overall discussion. Write a note on 0 point energy and quantization of energy, and also like non-quantization of energy, and all these kind of question can be asked. So apart from all this overall discussion, here the some of the references which you can refer for more details. You can see the online resources like Swayam portal, NPTEL videos, and many more books for the reference. You can refer it out. And now I thanks you all for listening this videos, and watching these videos and listening this videos. Thank you so much. Thank you.